Imagine a system given a highly complex logic puzzle. It delivers the correct answer, but if you look at the scratch pad, the math fails completely. One benchmarked system passed perfectly, yet inside its trace log, it ignored contrary evidence 7 times, relied on an untested claim, and held a fixed belief. Across all tests, 68% ignore evidence, and 71% never update beliefs. These systems are actively generating hypotheses and proposing therapeutic candidates, and they are receiving massive praise for those end products. Achieving a valid scientific outcome does not guarantee the system actually performed science to get there. Welcome to Bearded AI Guy. The human architect, whose writing on AI engineering I highly recommend, flagged this specific research to me as the most confrontational benchmark paper of the year. The paper is titled, AI Scientists Produce Results Without Reasoning Scientifically, released through the Corral project by the Jablonka group. The industry currently evaluates AI agents by grading their final output. We look at a generated draft or a code snippet, see that it works, and assume the correct output proves a sound reasoning process. Labs are shipping branded AI scientists at an increasing pace, claiming autonomous research capabilities, while our evaluation methodologies have failed to keep up with the marketing. This paper argues that task completion and scientific reasoning are entirely separate variables. Once you measure the process itself, the results expose an uncomfortable reality about how these models actually operate. To understand why this matters, look at the escalating claims from the past 2 years. Agent Laboratory claimed end-to-end research assistance. The AI scientist pushed peer-reviewed manuscripts, and Robin delivered wet lab-validated therapeutic candidates. The Corral benchmark was built to interrogate those massive claims. Instead of just checking if the final answer is right, Corral treats every step of the agent's internal trace log as an epistemic object that can be weighed and measured. The evaluation tests 3 frontier base models, GPT-4o, Claude 3.5 Sonnet, and GPT-OSS-120B, wrapped in 2 distinct scaffold families, React loops, and structured tool calling. This diagram shows Corral's core operational methodology. Every trace is annotated into a strict 6-node directed graph: hypothesis, test, evidence, judgment, update, commitment. That is the benchmark's definition of disciplined scientific reasoning. When you force an AI to answer to this rigid epistemic graph, instead of a simple pass-fail metric, the entire leaderboard changes shape. Think about a student who aces a multiple-choice exam purely at pattern-matching past test structures. The student produced the correct output, but checking the final score tells you absolutely nothing about their actual comprehension of the material. Corral maps this exact dynamic mathematically. It treats task completion and scientific reasoning as entirely independent variables. Take the benchmark's Q2O workflow task. An agent can execute 9 perfectly clean tool calls and score a 1.0 for success, yet its internal reasoning trace is completely marred by fixed beliefs and ignored evidence. High outcome metrics cannot be used as proxies for reasoning capabilities. Real scientific reasoning requires specific habits. You change your mind when the data refutes you, and you verify your beliefs with multiple convergent tests. The bad habits of pseudoscience involve committing to an answer prematurely and actively ignoring data that contradicts your initial guess. Corral categorizes these behaviors into a technical taxonomy, mapping agent trace logs into 7 productive patterns and 11 anti-patterns. Refutation-driven belief revision, dropping a hypothesis when contrary evidence appears, occurs in only 26% of runs. Convergent multitest evidence is even rarer, appearing in only 7% of runs. These failures are not edge cases or minor prompt bugs. This is the dominant behavioral signature of modern frontier models. If a race car is fast, you have to determine whether the speed comes from the engine block itself or the surrounding chassis. AI engineering teams spend vast resources building complex scaffolds around base models, assuming that sophisticated multi-step orchestration creates the reasoning capability. To test this, the researchers used a 2-parameter item response theory model fed into a Bayesian generalized linear model to mathematically isolate where agent behavior actually originates. This stacked bar chart shows the explained variance in agent behavior. The base model accounts for 41.4% of the variance. The scaffold explains just 1.5%. Elaborate React loops and structured tool calling pipelines are merely second-order effects compared to the base model's inherent prior tendency to either gather or ignore evidence. Complex engineering pipelines cannot patch or create foundational epistemic rigor if the underlying base model lacks those priors to begin with. Genuine understanding remains stable across multiple attempts. Lucky guessing quickly falls apart. The researchers used trace intervention to test this. They injected partially successful trajectories into fresh agent runs to measure reliability across repeated trials. The results diverge sharply based on the task. Trace injection successfully rescues simple workflow operations, but it completely fails to rescue complex, hypothesis-driven domains. Look at this graph plotting the pass to the decay metric. For hypothesis-driven tasks, reliability plummets below the 0.05 threshold by trial 4 to 6. If handing an agent the right answer halfway through a task still doesn't lead to a reliable success, the failure isn't a prompting error. Base models mishandle evidence under uncertainty. Their occasional initial successes on hard problems are driven by brittle pattern matching, not logic. This benchmark does not claim that current scientific agents are useless or that they are incapable of generating valid, helpful text. It exposes a much deeper gap. An output being useful is not mathematically or scientifically the same as it being justified. When you evaluate an AI system, you need to ask two questions. Did it succeed? And did the trace log contain the epistemic moves to make that success trustworthy? Trustworthy moves look very specific. They require a hypothesis that is actually put at risk by testing, evidence that is genuinely absorbed, and beliefs that tangibly update in response. If a system achieves a useful outcome without justified reasoning, it is merely automated text generation masquerading as science. If this reframed how you evaluate AI systems, subscribe to Bearded AI Guy. I'm working through the research that is quietly reshaping the agent landscape, one paper at a time. Drop your take in the comments. Does this data point to a benchmark failure, a scaffold failure, or a base model failure? I want to see where you land. Huge credit to the human architect. Their work on AI agents in action is the primary resource you should read for the applied side of this engineering debate. I'll leave you with this. A hypothesis that is never at risk is not a true hypothesis, and a belief that never updates is not a belief. An output that succeeds without reasoning is not yet science. See you in the next one.